Now let's move ahead with using Sklearn Library. So simply put, you can use Sklearn Library to automate everything that we have seen in code, calculating TF, then calculating IDF and multiplying them. So simply what you can do is call TF IDF vectorizer. So here we are importing TF IDF vectorizer from sklearn feature extraction.txt. And here we are initializing TF IDF vectorizer with analyzer as word. So this analyzer is almost like splitting the tokenization that we have seen, whether to do it on word level, etc. And we are giving the stop words as English. So the TF IDF vectorizer internally uses stop words in English from NLTK, etc. So whatever we did, which is removing stop words, then splitting and tokenizing, all those things are internally done automatically with this. Now the powerful thing is that you can go to this link right here and you will realize that there are several different types of analyzers. We are using word, but you can use character and other things, etc. Secondly, the stop words we have given English, which is automatically taken from NLTK, etc. behind the scenes. But instead, if you have, let's say, a custom stop words list, you can give that custom stop words list here. And as I mentioned, you can give a token pattern yourself. So you can give your regular expression yourself here. And the other thing is n-gram range. So here we are using only one, which is splitting on individual words, but you can give n-gram. Let's say if you give 1,2, that means it will take unigrams and bigrams. If you give 1,3, it calculates on all unigrams, bigrams and trigrams, everything. So there are several things that you can control here, which is giving stop words, custom stop words, or giving a custom regex pattern, regular expression pattern to split, or giving a custom n-gram range. So whatever we have seen in theory and code above, we can incorporate those here with multiple parameters. As you can see, you can customize the parameters here, but for simplicity's sake, we are just going to give this, which is analyzer word and stop words as English. But you can go ahead and very welcome to experiment with everything that we have learned above, which is n-grams and custom regex and other things. And what we are doing here is calling this function fit with the column of plots. So as you've seen previously, we have the plots column here. So almost 3,340 plus movies. So we are just giving this data frame column of just plot, and what it will magically do is, as soon as you call fit, this function fit calculates all the unique words like we have already done above, the 55,000 plus unique words after removing the stop words. And for each of the unique word, it will calculate the IDF value. We have also done that in code, going through each of the unique word and calculate the inverse document frequency of each unique word, because that is calculated for the whole corpus once. So with just one single simple line, we are removing the stop words, we are calculating all the unique words, and for each unique word, we are calculating the IDF, inverse document frequency of that unique word. So everything is done in just one single line here. Great. And now once you calculated that, you should be able to see all the unique words or tokens that you have calculated from TF IDF vectorizer, right? So that simply you can get those from get feature names function. Let's print this. So the words, so these are all the unique words that you see. Of course, when you split based on space and tokens, you will have words as well as numbers. If you just scroll, you'll see all the words ordered: cityscape, civilian, and geographies, judicious, etc. You can see all these words. So it's almost like there are almost 47,864 columns. So those are the features. And what that means is, if you give any movie plot, let's say Batman Begins, V for Vendetta, or any movie plot, that plot is going to get converted into this vector of length 47,864. That is the uniform vector that we are going to create. Of course, most of the values will be 0. Only those words which are present are going to have TF IDF values. But simply you can just call these get feature names and get all the features. Now I have mentioned that once you call fit, the IDF values are calculated. Can we just see those values? Yes, absolutely. You can just call this .idf underscore and you can see all the IDF values that are calculated. Previously we calculated that with code ourselves, but right now for every given word, that is for every given column, the corresponding IDF inverse document frequency value is also calculated. Now let's see another interesting function. Instead of fit, if you call transform, what's going to happen is that fit just calculates only IDF, inverse document frequency. What transform does is actually it will calculate the complete TF IDF. That is, it will calculate term frequency and multiply with inverse document frequency and create a full matrix. Let's just run this. And let's print the shape of this. So the shape of this is actually 3379 by 47864. So it has calculated the TF IDF vector for all the movie plots, where these are the rows. So each row corresponds to one single movie plot, and there are 47864 columns. Those columns correspond to the unique words or features in the whole corpus. The corpus consists of combined words from all the movie plots. Now let's just see that in a data frame so that it is very clear for us. Let's run this. So we can combine the transform output and append the columns, that is the feature names, and as you can see, this is how it looks. So there are almost 47,000 columns like this. You cannot see the middle columns, but you can see there is a ... and 0 corresponds to the first movie plot, 1 corresponds to the second movie plot, etc. As you can see, most of the values are 0, but you might not be able to see, but there are some values in here. For example, see the 10th movie plot, and 000 is a column. What does this mean? In the 10th movie plot, the TF IDF for 000 word is 0.04867. That means our library would have calculated the IDF, that is inverse documentary, for 000, and it calculated the term frequency of 000 in the movie plot 10. Then it multiplied TF with IDF and the value is here. Similarly, you can see that some values are non-zero, as you can see. And how do you get vector for a given movie plot? For example, let's say Batman Begins is 20 or something like that. How do you get the vector, TF IDF vector for Batman Begins? Simply you just take this whole and you get almost 47,000 plus features, that is columns. So you get almost 47,000 plus features, that is just a list of 47,000 values, 47,000 plus values, and that's the feature vector, that is the TF IDF feature vector for the 20th movie or 21st movie. depending on the indexing. And that's pretty much it. Any movie plot can be converted into a long vector, sparse vector of 47,864 length, and that's the TF IDF vector. So that's the uniform TF IDF vector that we calculated. So no matter how big or small the movie plot is, the vector is uniform and is of fixed length 47,864. And it's a sparse vector because only some values are non-zero. And one of the problems with TF IDF is the sparse vector itself. So you will see in advanced algorithms like sentence transformers, etc., you will have a fixed vector of 764 dimensions or 368 dimensions, etc. No matter whether your movie plot is long or short, you'll have a fixed vector. Instead of having a long sparse vector, you will have a dense vector that is shorter in size and fixed. What are the advantages of shorter vectors is basically you need to do comparisons. Now if you are comparing 47,864 vectors among each other, the computation also increases accordingly when doing comparisons. Whereas if you have a smaller vector of dimensions, let's say 300 or 400, you can do faster comparisons, etc.